And actually, we're going to come back to stoichiometry, so in a later part, I don't know, Friday or next week. But one of the things that's important, basic things in Introduction to General Chemistry, is to visit solutions and how we talk about solution, how concentrated the solution is. So what a solution is actually two or more things that are physically mixed together. So solutions can be separated back out to their components by some sort of physical means. So we kind of generally think of like, this is my beaker, I'm going to make my solution. What I have a lot of, that's called the solvent. And what I'm going to add is called the solute. And then together, they make the solution. And my abbreviation for solution is SOL''N. Now, if the solvent is water, we call that an aqueous solution. And so we've kind of seen the AQs. Okay, that simply means that if we see that in a chemical equation, it means that you have that thing dissolved in water. So we generally think of, if I'm thinking of this scenario, we think of my solvent is liquid and I'm going to dab some solid solute in there. But that's not always the case. We could have a liquid solvent and a liquid solute, such as the case with vodka, which is mostly ethanol, which would be the solvent, and solvent, and the solute would be water. We could have basically dissolved some sort of gas into a liquid solvent. A good example of that is pop. Okay, carbon dioxide has been infused into the sugar water, basically, which is the solvent. We could have a solution of gases. As we're walking around this room, it's a sea of gas, mostly nitrogen, a little bit of oxygen. So in that case, I guess nitrogen would be kind of the solvent gas, and oxygen in that case might be considered a solute. And I think I mentioned this the other day, that as we're dealing with different grades of metal, actually metal is a type of a solution in which everything that's dissolved together just happens to be solids. Okay, so they're frozen together. Excuse me. So, like I said, I want to spend a little bit of time talking about how do we say how concentrated the solution is. And in general, we talk about, we're going to be talking about kind of a ratio, so amount of solute per a given amount of solution. Oh goodness, I can't spell, but something like that. So how much solute is there in a given amount of solution? We aren't going to, in this class, go to another important way of saying how concentrated a solution is, and that is the amount of solute per a given amount of solvent. That's another important way. Now, the fact that we are going, I'll get back to that point. So here's some terms that you probably have heard about. A concentrated solution means I have a lot of solute dissolved in my solvent. A dilute solution means there's not much solute dissolved in my solvent. Oftentimes when we're dealing with environmental samples, they are relatively dilute, but honestly it does not take much of some contaminants to play havoc with biology. So dilute is not necessarily a good thing. I mean, depending on how dilute it is. So the two ones I want to hit, there's a third one, I'll maybe come back to it, but I want grams of solute per liter of solution, or I want moles of solute per liter of solution. Okay, in both of those cases. Now, here's where, the fact that the two ones we're looking at with regard to describing solution concentration is grams of solute per liter of solution, moles of solute per liter of solution. One of the things about volume, and you know this if you ever tried to quickly, we've talked about how water will expand as it transitions from a liquid to a solid. So we are kind of fighting this sort of water will change volume when it changes temperature. So that's okay. We'll just, a lot of times when you work chemistry problems talking about solution concentration, they will give you the temperature. So let's work a problem, or two, three. I'll just kind of add to this beaker I've got here. It says, what is the concentration in grams per milliliter of a solution that's made by dissolving sucrose in the amount of 32.3 grams in enough water to give a final solution volume of 225 milliliters? So I would do 32.2 grams of solute. It happens to be C12H22O11. And the total volume, I think I'll change this. Let me just put it right here. The total solution volume is 225 milliliters. So this is where I say don't make it harder than it is. If our target is grams per milliliter, all I'm going to do is take those grams and divide it by, actually it's grams per liter. I'm going to take those grams and divide it by those milliliters, and then I'm going to, when I say fix the milliliter term. So solution, no pun intended. If our target is grams per milliliter, so I'll put usually question mark, grams per, I keep saying milliliters, grams per liter, that's our target. We start out with putting the grams of the solute over the total volume of solution, and then we have talked about how we can kind of, it's a factor label process of working problems. If I want to get units of liters in the denominator from milliliters, I can introduce the relationship between milliliters and liters. We know that 1 liter is exactly equal to 1,000 milliliters. We know for every equivalency statement, you can make it a conversion factor. So that's all I've done here. Now I've done it this way, so units of milliliters will cancel. I'll be left with units of liters. So we need to round to what, 3 significant figures. So your calculator will round to 3 sig figs, will give 144, and units would be, I would probably write it like this. Units would be grams per liter of the solutes. So a follow-up question to the same solution would be this. What is the molarity of this solution? So now my target is molarity is moles of solute per liter of solution. And actually I'm going to kind of piggyback on my 144 grams per liter to get to my moles per liter. I know I can get from grams to moles using the molar mass. So don't forget, and I don't know, I think I did maybe mark it on you. Was it yours or his? But you always have to show you have to show calculating your molar mass before you use it as a conversion factor. So the molar mass for this compound, I take 12 times 12.01 plus 22 times 1.008 plus 11 times 16.00, and you're looking at a molar mass of 342.30 grams per mole. Again, you can't go wrong unpacking that. And so what that would mean is 342.30 grams per 1 mole. So don't forget that's what that means. So I said we were going to piggyback on the 144. So if we bring back in what we know about the solution in terms of grams of sucrose per liter of solution, and then introduce the molar mass as a conversion factor. Notice in this case, I'm going to have to take the inverse of the molar mass because I want grams of sucrose to cancel. So if I simply introduce 1 mole of C12H22O11 over 342 grams of the compound, C12H22O11, the grams of compound will cancel. I'm left with moles of compound per liter of solution. It's all about the units. It's not about the base. So we round it to 4 sig figs and 3 sig figs. Rounded to 3 sig figs, you're looking at a number of 0.419. and then units would be moles of compound per liter of solution. But this is where actually this big M means molarity or molar concentration. So I probably would just jump right to 0.419 molar of the compound, C12H22O11. So two ways of describing solution concentration that I want to worry about for y'all this semester. My video doesn't work, but that's okay, because I have an image from your textbook that kind of shows you how would you, if somebody said, I need a solution and it has to be this concentration, what does that look like? And specifically, somebody said, was tasked with coming up with a 1 liter solution of 1 molar sodium chloride. Well, this piece of glassware is called a volumetric flask. I think we talked about these before. And you can, the thing about volumetric flasks is they will have a, they would like to have a to contain value on them. So this one must have a 1 liter value on it. It's probably 1.000 liters. And it means up at that mark, that's the volume I have in that volumetric flask. So it's just one mark, one gradation. So somebody went and said, well, if I need it 1 molar, and this is 1 liter, so all I need to do is add 1 mole of the compound, sodium chloride, to this. So they went and they knocked out the molar mass from the periodic table for sodium chloride, 58.44 grams per mole. So my point here is, notice that they are going to add the dry powder first. They'll probably take this and rinse it out with the water they're going to use next. So then one of the tricks to making solid solution is you don't add water up to the neck, especially if it's in the volumetric flask, because you need swishing room. So you add just enough water to kind of swish it around, get it all dissolved, hopefully. Of course, you can see they're using a wash bottle. And then the last trick is to go ahead, once it's dissolved, basically, go ahead and add water up to the calibration mark. A really common mistake that I am better at now, but if you don't do, after you've added water to bring it up to the calibration mark on your volumetric flask, you have to invert it a few times. Otherwise, what you've set somebody up for is basically having a concentrated solution down here and dilute here. So one last mix is a good idea. So these will be due on Friday. Not very many of those left. Notice, and again, on the test, I'll be careful for your Unit 4 exam and say you have to show all work and all that. So make sure that you're doing that with your homework too. All right, so let's look at the next part. So we can use solution concentrations then as conversion factors, and we'll show you what that means. And so conversion factor is going from some units to other units. And you're like, well, how would I know how I can use my solution concentration as a conversion factor for what? Well, look at the units of your concentration. So if the units of your concentration are grams of solute per liter of solution, that's what you can go back and forth between. If the units of your solution concentration are moles of solute per liter of solution, that's what you can go back and forth between. I'm going to go ahead and throw one more up here. We've been talking since Unit 1 about this idea of mass percent. And if somebody, mass percent or mass fraction differ by a factor of 100. So if somebody gives you, I'll show, let's see, X weight percent, and it's a solution. So what that means is that we can unpack that. That means that you would have X grams of solute per 100 grams of solution, okay? And we can use that then as a conversion factor. So let's see. So in this case, actually someone's already prepared the solution. The solute is sodium chloride. The concentration is given in grams of solute per liter of solution. So what you're going to see actually on the next slide is I'm going to take that 14.3 G/L. I'm going to actually unpack that. I should never see you work a chemistry solution concentration problem where you just leave it G/L, because it's like G/L, what does that mean? So in this case, that means 14.3 grams of the solute, NaCl, per 1 liter of solution. So if you get that down, then the problem really isn't too hard. The first term actually is going to be my 22.3 grams of NaCl over 1. And then notice what I'm after is to try to get to volume of solution. So, looks like this. So like I said, what does the 14.3 G/L mean? It means grams of solute per liter of solution. You're gonna need to unpack it to use it. For this particular solution, we could say that in 1 liter solution, you're gonna have 14.3 grams of NaCl. We could also flatten it out. It's like a physical property of this particular solution. So, kind of showing you the diagram of how we get from grams of NaCl to volume of solution. We're going to use the concentration that was given. So if we make our first term 22.3 grams of NaCl over 1, notice then we've been talking a lot about this, that if I want grams of NaCl to cancel, I'm going to have to put it in the denominator of the next term. So I need to use the solution concentration this way, where I put 1 liter of solution over 14.3 grams of NaCl. Grams of NaCl cancel, we're left with units of liters of solution. That's perfect, great volume. And we need to round according to sig figs, so 3 sig figs. So you're looking at 1.56 liters of solution. That's it, Mom. Okay. I think I've mentioned this before, but the factor label method sometimes will only work as well as you are using your labels, your units. You're going to need to be careful and be explicit sometimes, like you've done with the stoichiometric calculations. All right, so let's work another problem. In this problem, the solute is potassium dichromate, K2Cr2O7. The molarity is given. And here on the next slide, you're going to see me unpack that molarity. I don't know how anybody could ever use that in a problem. What that means is we have 0.255 moles of the solute, K2Cr2O7, per 1 liter of the solution. All right, experiment calls for 0.015 moles of K2Cr2O7. How many milliliters is that? So our first term actually is gonna be that 0.015 moles of K2Cr2O7 over 1, and then I'm gonna use this to my benefit. Now, you're gonna see on the next slide though, if I use this to my benefit, I'm gonna get the volume of solution in terms of liters, and don't forget, looks like I need to do one more thing, because I don't want to leave it in liters of solution. I want milliliters of solution. So again, anytime you see that big M, that means molar concentration. That would be moles of solute per liter of solution. And we can kind of think of that as a puzzle piece that we can use however we need to. All right, so strategy is, simply we're going to go from moles, the target moles, we're going to use the molarity to get to the volume in liters. And like I said, don't let it throw you off. And I don't want volume in liters, I want volume in milliliters, and we know how to do that. We need to go back and remember that 1,000 milliliters is equal to 1 liter to finish the problem. So the first term is the moles of K2Cr2O7, 0.015 moles. I usually put that over 1. And then the second term is what I call the flipped version of the molarity. Since we want moles to cancel, we're going to put units of moles of K2Cr2O7 in the denominator of the second term. And in the numerator of the second term, then we have 1 liter of solution. We're almost done then. We're going to use this equality up here. 1,000 milliliters is exactly equal to 1 liter. We want liters to cancel, so we're going to put, what, 1,000 milliliters of solution over 1 liter of solution. So moles of K2CR2O7 have canceled, liters of solution have canceled, and we're left with units of milliliters of solution, which is perfect. In this case, we're only allowed in our answer 2 significant digits because I have 2 here. This one is important, it's a placeholder, but it's not significant. So 2 sig figs, we're looking at 59 milliliters. We're gonna have time, it looks like, to get to the section, and I'm gonna talk about what's called titrations. So actually, these sort of calculations are important in titrations, and in titrations are important in what we say assaying or getting to determining the solution concentration. So, all right, let's do, I think, just one more. Different solute, calcium chloride. I'm given the volume and I'm given the molarity, and I'm supposed to say how many moles of calcium chloride are running around in that volume given that molarity. So again, I'm going to take that 0.108 m, I'm going to unpack it. 0.108 moles of the compound CaCl2 per 1 liter of solution. And there's a pattern here. When I work these problems, I hold my molarity for a later term. One of my first terms is going to be actually what's specific to this problem, 75.0 milliliters. Notice that if that's my first term, I can't introduce molarity right away because I have milliliters instead of liters. So you can see actually my strategy is going to be to go from milliliters to liters using 1,000 milliliters, exactly equal to 1 liter. By the way, I mentioned this earlier in the course. It's a really common mistake to accidentally say 1 milliliter is equal to 1,000 liters. Don't do that. So once I've got milliliters to liters, then I can go ahead and go from liters to moles using the molarity. So this problem looks like this. If I start with that 75.0 milliliters of solution over 1, I want units of milliliters to cancel. So I'll put 1 liter of solution over 1,000 milliliters of solution. And then I'm ready to go ahead and introduce molarity. And actually, this would be the non-flipped version of molarity, wouldn't it? So if I just simply introduce as my third term 0.108 moles of CaCl2 over 1 liter of solution, then my units work out. So let's see what we got. Milliliters of solution, cancel. Liters of solution, cancel. I'm left with moles of solute, which was actually my goal. And I'm allowed 3 significant figures because that trailing 0 after the decimal counts. So 3 sig figs there, 3 sig figs there. And that's why my answer actually, I have these placeholder zeros, they don't count as significant. It looks like I have a trailing 0 after the decimal. So 0.00810. And then of course the units would be moles of CaCl2. Cool. Okay. Let's do another one. This would be a practical one if somebody says, give me 125 milliliters of this solution, and this is my target molarity, and you're supposed to go weigh out the solute. So what mass of glucose would you dissolve in 125 milliliters to give you 0.432 moles per liter of glucose, which the formula is C6H12O6. So let me go ahead and write this one up here. Change that to solution. pins. Okay, so I am adding C6H12O6. So question mark grams that I need to add in my solution volume is 125 milliliters. And my target molarity is 0.432, I'll go ahead and say moles of sucrose, C6H12O6 per 1 liter of solution, okay? So in this case, can't remember how I did my slides. We are going to go from the volume, which is given in milliliters. Okay, basically going to use this volume and the molarity to get to moles. And then from moles, we're going to use the molar mass to get to grams. But notice that my volume is given in milliliters, so I can't use the molarity directly. So I need to go ahead and convert milliliters to liters. Using 1,000 milliliters is exactly equal to 1 liter solution. Then I can introduce molarity to get to moles. And then I can go ahead and once I have moles, I can use the molar mass to get to grams. But again, don't forget to show that molar mass calculation. So here we go. Looks like I didn't show that molar mass calculation. So my first term is the volume of the solution, 125 milliliters over 1. And then I want to get to liters, so I'll put 1 liter of solution over 1,000 milliliters. And now I'm ready to introduce molarity. I'll use the unflipped version of molarity, that 0.432 moles of C6H12O6, excuse me, over 1 liter of solution. And I apologize, I did not show you my molar mass calculation. But if you were to use a periodic table to come up with the molar mass of C6H12O6, you would come up with 180.16 grams per mole. So if I put as my fourth term, the 180.16 grams of C6H12O6 for 1 mole of C6H12O6. So unit-wise, my milliliters canceled in the first term. My liters canceled from molarity, that gave me moles. And then from molar mass, my moles canceled and left me units of grams, which is perfect. Well, it's looking like 3 sig figs in the first term, no uncertainty brought by the second term, 3 sig figs in the third term, and a whopping 5 sig figs in the molar mass. So 3 sig figs, you're looking at 9.73 grams of C6H12O6. Again, another potentially very practical problem. You become a lab tech. So these will also be due on Friday. I think that's as far as I wanted to get today. So you have time to... Or not.